లైవ్ ఇవన్నా చేశాను
ఇచ్చేసాయి. ఎవ్రీథింగ్ ఇస్ ఫైన్ కదా?
ఇచ్చేసాను సార్ లైవ్ ఇచ్చాను.
ఓకే, స్టార్ట్ చేస్తాం. Good afternoon, friends. I once again welcome you all to this online session of GATE coaching classes being organized by Jawaharlal Nehru Technological University, Anantapur, Kakinada, and Yogi Vimana University, Kadapa. So today's topic we are going to discuss is about torsion. Before that, I would like to answer some of the queries raised by some students from the previous class. Majority of the issues are regarding buffering of video. So as far as our side is concerned, our network connectivity is good and there is no buffering taking place in the video or the audio. There is a separate monitoring cell in the university headquarters. They are sitting there and watching the entire video. So here we are not facing any buffering or we are not observing any audio break. Because you are at some rural place or some place where your connectivity may be poor, because of that you may be experiencing buffering. But there is no problem. The videos which we are uploading to the YouTube, they will not have any buffering. They will be very clear. The audio and video will be very clear. So for any problem, you can look at to the videos which are uploaded to the YouTube. So these videos will be available to you for 200 days. So you can watch these videos anytime. So there is no problem regarding the buffering. So on our side, our technical team is monitoring this, and if any problem comes, they are reporting to me. But as far as our side is concerned, there is no technical issues. So the problems you are facing, the buffering problem or audio break you are facing, maybe mainly because of the poor connectivity at your end. Probably you were watching in a mobile, or you are watching from a rural place or a place where there is no signal. So except that, there is no issues. Yesterday, not many technical questions are posed. So without spending much time, I would like to go directly to the topic on torsion today, because it's a very big topic and very important topic also, torsion. So let us try to spend more time on torsion today. In our previous classes, we understood bending moment. And we also understood how to find out bending stresses across the depth of the beam. So, because of the bending moment, tensile stresses and compressive stresses will occur in the beam. Okay, there are tensile stresses as well as the compressive stresses that occur in the beam due to bending moment. Okay, but there is one layer which will not undergo either tension or compression. Such layer we call it as the neutral axis. And in bending, we have seen that the neutral axis always passes through the centroid of the cross section. So at the neutral axis, the stress is equal to 0. The strain is also equal to 0. So we also seen that in bending, in simple bending, the strain distribution is linear and the stress distribution is linear. That is, the maximum bending stress occurs of the extreme fibers, and at the neutral axis, the bending stress is equal to 0. So in a similar way, now we will try to understand how to find out the stress distribution due to torsion. Shafts for power transmission, shafts that are used for power transmission is a very major application of torsion problem. So let us see how to analyze a shaft which is subjected to torsion and how to find out the stresses. So first let us try to understand what is torsion or twisting moment. Torsion is also called as twisting moment. And please note that twisting moment is also force multiplied by distance. Bending moment is also force multiplied by distance. It is also a moment. Torque also is a moment. So what is the difference between bending moment and twisting moment or torque? We have to first understand that very clearly. So if you take bending moment, if this is the axis of the beam, if this is the axis of the longitudinal axis of the beam, and if we are applying moment in a plane perpendicular to the axis of the beam, see this is the axis of the beam, and you apply a moment perpendicular to this axis, this moment causes bending. This moment causes bending. On the other hand, see this is the longitudinal axis. Now you apply moment in a plane which contains the longitudinal axis, See now, if you apply a moment like this tries to cause the twisting. This is twisting. So this, if you apply moment in this direction, in this plane, it causes twisting. If you apply moment in this plane, it causes bending. So you need to understand the difference between bending and twisting very clearly. So if a moment is applied in a plane perpendicular to the longitudinal axis of the beam, it will create bending. And if you apply moment in a plane containing the longitudinal axis, it will create twisting. This will create twisting. So such a moment is called as a twisting moment or torque. Twisting moment, torque or torsion. So generally, the shaft transmitting torque or power, I-beams, portico beams, beams curved in plan, and closed coil springs are subjected to twisting moment. Those closed coil springs are subjected to twisting moment. So here I have given you some of the examples. If you take first a shaft which is under torque, okay, this is a shaft which is fixed at the left end here, and a torque is applied at the free end. Okay, a torque is applied at the free end. This is the longitudinal axis of the shaft. This x-axis is the longitudinal axis of the shaft. So this is length of the shaft is L, and generally we analyze the torque by considering a section x, a section at a distance of x from fixed end of width is equal to dx. So this is another shaft which has got internal torque. So if you take a small strip of dx and try to draw this strip, you can see equal and opposite torque is applied at the ends. So to balance this, internal torque T is also developed. So this is how the deformation takes place in a shaft subjected to torque. So you can see the layer like this is getting twisted. The layer is getting twisted with respect to the longitudinal axis. So this is called as angle of twist. Angle of twist. Just like deformation in bending, here we get the deformation as angle of twist. Due to torque, there will be angle of twist. Due to bending moment, there will be strain, either extension or compression. Due to bending moment, there will be either elongation or compression. But due to twisting moment, there will be angle of twist. Similarly, here I have shown the variation of shear stress due to torque in a cross section. Please remember, twisting moment or torque produces purely shear stresses because we are applying the moment in a plane containing this longitudinal axis. So it causes twisting. So the layers get twisted. So only shear stress gets developed. Okay, only shear stress gets developed. See, this is the layer and we are trying to twist. So there is a parallel movement. So that's why only shear stress will be developed. So because of the twisting moment, there will be only purely shear stress. Because of bending moment, we get compressive stress and tensile stresses. So there, if the sagging moment is applied above the neutral axis, we get compressive stress. Below the neutral axis, we get tensile stress. Whereas in twisting moment or torque, due to torque, pure shear stresses will be developed. Due to torque, pure shear stresses will be developed. There will not be any other stress other than shear stress. So please remember, bending moment causes compressive stress and tensile stress, whereas the twisting moment causes pure shear stress. So the variation of shear stress at a cross section, if you see, consider a shaft of radius r, you can see the maximum shear stress occurs at the top fiber, maximum shear stress occurs at the extreme fiber, and it is 0 at the neutral axis. 0 at the neutral axis. This is the variation of shear stress in a circular torque. To analyze a torque subjected to certain, analyze a shaft subjected to a torque, certain amount of torque, we also make certain assumptions, just like what we have done in simple theory of bending. Similar assumptions are made even in case of torsions, theory of torsion. Okay, the first assumption is the material of the shaft is uniform throughout. The material is uniform and homogeneous. Generally, that's a very common assumption, whether it is bending theory or it is torsion theory. Circular sections remain circular even after twisting. So this is very important. Circular sections which are circular before twisting, they remain circular even after twisting. So this is very important. Plane sections which were plane and normal before to the twisting, they remain plane and normal even after twisting, and they will not twist or warp. The plane sections will not get twisted or warped. So this is the very important assumptions again in theory of torsion. Because of this, the twisting, the angle of twist is proportional to the distance from the neutral axis. Because of this, the angle of twist is proportional to distance from the neutral axis. Like in bending, the strain is proportional to the distance from the neutral axis. So similarly, plane sections remain plane and do not twist or warp even after twisting moment. Stress is proportional to strain, and we are operating within the elastic limit. We are operating within the elastic limit. Shaft is loaded by twisting couples in planes that are perpendicular to the axis of the shaft. This is natural. Twist along the shaft is uniform. We are assuming that in a given shaft, the twist is uniform. The twist is uniform along the length. The distance between any two normal cross sections, they remain the same after twisting also. This is all to make the theory somewhat simple. So with these assumptions, we derive a torsion equation which is similar to a bending equation. Okay, bending equation was m by I is equal to sigma by y is equal to E by R. Sigma by y is equal to E by R. So similarly here, T by J is equal to tau by R is equal to G theta by L. T by J is equal to tau by R is equal to G theta by L, where T is called the twisting moment or the torque. J is called polar moment of inertia, similar to what we have read, the moment of inertia. I is the moment of inertia there. J is the polar moment of inertia. Tau is the shear stress at a distance of y from the neutral axis, or at a distance of small r from the neutral axis. Capital R is the extreme fiber. Capital R is the radius. Capital R is the extreme fiber distance. So from this, L is the length of the shaft, G is the modulus of rigidity or the shear modulus, theta is the angle of the twist. Theta is the angle of the twist. So from this equation, this is a very popular equation. T by J is equal to tau by R is equal to G theta by L. T by J is equal to tau by R is equal to G theta by L. This is a very popular equation called torsion equation. So here, very important thing is, if you see from this T by J is equal to tau by R, T is equal to, the torque is equal to shear stress tau multiplied by J by R. So T by J is equal to tau by R. So from this T is equal to tau into J by R. J is called the polar moment of inertia of the section. The polar moment of inertia of the section. So polar moment of inertia is equal to Ixx plus Iyy. The polar moment of inertia is equal to Ixx plus Iyy. Whereas the moment of inertia Ixx we have used in bending theory. Here we are using polar moment of inertia. So from this formula, T is equal to tau into Zp, where Zp is called the polar section modulus. The polar section modulus, Z we have defined as I by Y. Similarly here, Zp is defined as J by R. Zp is defined as J by R. Zp is called polar section modulus. Polar section modulus. So hope this is very important. This equation is very important. You understand this. T by J is equal to tau by R is equal to tau is the shear stress at a radius of r from the center, theta is the angle of twist, L is the length of the shaft, G is the modulus of rigidity. So if you understand, we get that the torque tau carried by a shaft is directly proportional to the polar section modulus. It depends upon the polar section modulus. For a given material, the torque carried is directly proportional to the polar section modulus, ZP. So that's what I have represented here. For a given material, the maximum permissible shear stress tau is constant. So that's why the torque is directly proportional to polar section modulus. So the torsional resistance of the shaft is proportional to the polar modulus of the shaft. The polar section modulus is the measure of strength of the shaft in torsion. So just like Z is the section modulus, is the strength of the beam in bending. Polar section modulus is the measure of strength of shaft in the torsion. Or otherwise, the torsion carrying capacity of a shaft depends directly on the polar section modulus. Now let us see how to find a polar section modulus for a circular section, a solid circular section and a hollow circular section. So if you take a solid circular shaft, of diameter d, the polar section modulus is equal to Ixx plus Iyy. Because it is a circular section, Ixx is equal to Iyy. So the polar moment of inertia, J is equal to Ixx plus Iyy is equal to 2I. Because Ixx is equal to Iyy for a circle. So, 2 into pi d to the power of 4 by 6 is equal to pi d to the power of 4 by 32. Pi d to the power of 4 by 32. So, the polar moment of inertia for a solid circular shaft of diameter d is equal to pi d to the power of 4 by 32. So, this is actually twice that of, it is half of, twice that of the moment of inertia. Moment of inertia is pi d to the power of 4 by 64. This is pi d to the power of 4 by 32. So J is equal to 2I. J is equal to 2I. Similarly, if we consider a hollow circular shaft whose external diameter is capital D and internal diameter is small d, then the polar moment of inertia J is equal to pi d to the power of 4 minus small d to the power of 4 by 32. Pi into small d to pi d to the power of 4 minus small d to the power of 4 by 32. So this is also same. Pi d to for J is equal to Ixx plus Iyy. Because it's a circle, Ixx is equal to Iyy. So J is equal to 2I. For a hollow circle, I is equal to pi into d to the power of 4 minus small d to the power of 4 by 64. That multiplied by 2 gives J, which is equal to pi into d to the power of 4 minus small d to the power of 4 by 32. So now knowing J value, we can calculate the polar section modulus ZP value. So for a given shaft of J and the radius R being constants, the polar section modulus ZP is equal to J by R. Radius, R is the radius. R is equal to capital D by 2 for a solid circular section. So pi d cubed, J is equal to pi d cubed by 32. Pi d cubed by 32 divided by D by 2. So this will give pi d cubed by 16. The polar section modulus is equal to J by R. J is equal to pi d to the power of 4 by 32. That divided by R is equal to D by 2. So we get Z polar section modulus for solid circular section ZP is equal to pi d cubed by 16. So same way for hollow circular section, the extreme the extreme R is equal to capital D by 2. So substituting capital D by 2, we get pi into d to the power of 4 minus small d to the power of 4 by 16d is the polar section modulus for a hollow circular section. So for a given material, the torsion carrying capacity of the shaft is directly proportional to this polar section modulus, which is pi d cubed by 16 for a solid circular section and pi d to the power of 4 minus small d to the power of 4 by 16d for a hollow circular section. So if you see from the basic torsion equation, T by J is equal to G theta by L. the angle of twist theta is equal to TL by GJ. The angle of twist in radians, theta is equal to TL by GJ. So if you take a shaft, for a given shaft, G, L and J are constants. G, L and J are constants. So G is the shear modulus, which is constant for a given material. L is the length of the shaft. For a given shaft, L is constant. And for a given shaft, J is also constant because its diameter is fixed. So J is also constant. So the angle of twist is directly proportional to the torque. The angle of twist theta is directly proportional to the torque. So for a given shaft, G, L and J are constant. So that's why the angle of twist is directly proportional to the torque T. We also define what is called as torsional rigidity. Just like the flexural rigidity, we define torsional rigidity. We know flexural rigidity is defined as EI. Similarly, torsional rigidity is defined as the product of G and J, the shear modulus and the polar moment of inertia. The shear modulus and the polar moment of inertia. So we know from this equation, T by theta is equal to Gj by L. T by theta is equal to Gj by L. Okay, T by theta is equal to Gj by L. So if you consider a shaft whose length is L and which has got a angle of twist of 1 radian. So if you substitute L is equal to 1, theta is equal to 1, Gj is equal to T, or otherwise the torsional rigidity is defined as the amount of torque carried by a shaft of unit length to produce an angle of twist of 1 unit. Angle of twist of 1 unit. So such a torque is called as the flexural rigidity. Sorry, torsional rigidity. We call torsional rigidity. Similarly, if you can see the shear stress developed in the torque, you can take the shear stress is tau by R is equal to T by J. So from this, tau is equal to T by J into R. T by J into R. Tau is equal to T by J into R. And you can see for a given shaft, J and R are constant. So tau is directly proportional to T for a given shaft. So these concepts are very important. You need to follow the concepts, nothing more. So the maximum shear stress occurs on the cross section of the shaft at its outermost surface. So if you see, the maximum shear stress occurs where R, this small r is maximum. This small r is maximum. So if you consider the radius, when small r becomes capital R, the maximum shear stress occurs, which is equal to G theta by L into R. So whether it is a solid circular shaft or whether it is a hollow circular shaft, the maximum shear stress occurs at the extreme fiber, the top surface, at the top surface of the shaft, on the surface of the shaft. These shafts are generally used for transmitting the power. So if you see a hydropower station, near a dam, or where the water is supplied to through penstocks. Penstocks are called pipes of very huge diameter. Penstocks are pipes of very huge diameter. So water under pressure, the water and pressure is given to the turbine. Water under pressure is given to the turbine. So the turbine, the vanes of the turbine are hit with water coming from the penstock. So because of that, the turbine rotates. The turbine rotates. So when it rotates, it cuts the flux. Okay, it rotates, it cuts the flux. So what we get is the electricity is generated. So this is transmitted. This power is transmitted by a shaft. Through mechanical rotation. So the amount of power transmitted by a given shaft is a very important topic. So the main application of the shafts is to transmit the power. Okay, to transmit the power. So when the turbine rotates, the vanes of the turbine, they rotate, the turbine rotates, and then the flux is got cut and the power is generated. So this power is transmitted by the shaft. So here we have to calculate what is the power that is transmitted by a given shaft. So we know the power transmitted is nothing but equal to work done by the torque. So let us say the shaft is rotating at a speed of n revolutions per minute. Okay, the shaft is rotating at a speed of n revolutions per minute. N revolutions per minute. So for 1 minute, how much distance it is rotating? For one circumference, it is 2 pi. Okay, for one circumference is 2 pi. So n revolutions it is rotating in 1 minute. So it is 2 pi into n. Okay, the distance the traveled is 2 pi into n. So the force is nothing but the torque here. So the torque is T multiplied by 2 pi n gives the work done by the torque. So the work done by the torque is equal to T into 2 pi n, where n is the number of revolutions per minute. Number of revolutions per minute, or it is also called as RPM. Revolutions per minute, RPM. So if power transmitted by the shaft is P kilowatts, so please see this, I am referring P in kilowatts. So here the work done by the torque is in Newton meters per minute. Okay, the work done by the torque is Newton meters per minute. But power transmitted is in kilowatts. So let us convert this into the same unit. So P into, if it is in kilowatts, so if you multiply it by 1000, if we multiply this with 1000, we get P into 10 cube Newton meter per second, because 1 watt is equal to 1 joule per second. 1 watt is equal to 1 joule per second. 1 joule per second, that means 1 Newton meter per second. 1 Newton meter per second. So this is P into 10 to the power of 3, or P into 1000 Newton meters per second. P into 1000 Newton meters per second. Or if you want per minute, I want Newton meters per minute. So multiply with 6. So 60,000 into P Newton meters per minute. So if this is the power transmitted, then work done by the torque must be equal to power transmitted. So you equate 2 pi n is equal to 60,000 P Newton meters per minute, from which the power transmitted by the torque T is equal to, the P is equal to 2 pi nt by 60,000 kilowatts. P is in kilowatts. So 2 pi nt by 60,000 kilowatts. So here, please remember, the units are very important when you apply this formula. When you apply this formula, units are very important. The power P is equal to 2 pi n by 2 pi nt by 60,000. Power is in kilowatts, and N is the rotational speed of the shaft in RPM. T is average torque or mean torque in Newton meters. You have to substitute in Newton meters. Torque is to be substituted in Newton meters. So torque is in Newton meters, N is in RPM, then we get power is equal to 2 pi nt by 60,000 kilowatts. If you want the same power in horsepower, HP, the formula is P is equal to 2 pi nt by 45,000 HP. 45,000 HP. So conversion from kilowatt to horsepower. So generally we use kilowatts. So P is equal to 2 pi nt by 60,000 kilowatts. You have to remember this, that torque is to be substituted in Newton meters. So generally when we calculate the carrying capacity, when for power, how much power we are transmitting, when you want to calculate the power transmitted, the T here used is the average torque or the mean torque. The T used here is the average torque or the mean torque. So when in the day of operation, we can't expect the torque to be same. Okay, we can't expect the torque to be same. There will be changes in the torque. So the total T1 plus T2 plus T3 plus T4 so on divided by N will give you the mean torque. Okay, will give you the mean torque. So at one time the torque will reach the maximum. That is called, we call it the maximum torque. Sometimes the torque becomes maximum at some point. So such a torque is called as a maximum torque. So average torque is there, maximum torque is there. So when you want to calculate the power transmitted, we use mean torque or the average torque. So here T is the mean torque if you want to calculate the power. If you want to design the shaft, if you want to decide the diameter, then we maximum torque into consideration. T will be as T max. Okay, T will be considered as the maximum torque. Why? When you want to fix the diameter, you have to fix it for the maximum torque. If you fix it for the average torque, then at some point the maximum torque comes, then the shaft will fail. The diameter is insufficient. So that shaft will fail. So when you are trying to find out the diameter of the shaft to carry the power, then we have to use maximum torque. On the other hand, if you are trying to find out the amount of power transmitted, you have to use the mean torque. As the average torque. So this concept you have to keep in mind very clearly. Maximum torque Tmax will be used when you want to find out the diameter. We want to design the shaft. When you want to calculate the power, you have to use average torque. That is what the concept here. So please remember P is equal to 2 pi nt by 60,000 kilowatts, where torque is in Newton meters, N is in RPM. So if a shaft is subjected to T Newton meters of torque is rotating at N RPM, it will produce 2 pi nt by 60,000 kilowatts of the power. So what are the stresses developed in the shafts? Let us have a look. Now already I explained you, due to twisting moment or torque, the stress developed will be purely shear stress. And this maximum shear stress occurs on the outermost surface of the cross section. That is on the surface of the torque. It occurs on the outermost surface of the torque. The maximum longitudinal shear stress occurs on the surface of the shaft and the longitudinal planes passing through the longitudinal axis of the shaft. So it's both are same. The maximum tensile stress, the major principal stress, occurs at planes 45 degrees to the maximum shear stress plane. These are already in the previous class itself I have explained. The maximum shear planes and the maximum major principal stress plane, they are at 45 degrees to each other. So same thing. Similarly, the maximum compressive stress will be at 45 degrees to the minor principal plane. Maximum shear stress in the cross section of the shaft is significant for stress for design. Yes, for design we always take the maximum shear stress. For most engineering materials, shear strength is small as compared to the tensile and compressive stresses. Yes. So let us now define what is called as modulus of rupture in torsion. Modulus of rupture in torsion is defined as the maximum shear stress required to produce a failure. Maximum shear stress required to rupture the shaft based on the ultimate torque. So that is called as a modulus of rupture. That is nothing but maximum shear stress due to ultimate torque. So which is nothing but T ultimate into R by J. Tau is equal to T by J into R. So same thing. T by J into R. That's all. Another very important, interesting topic in shafts or the torsion theory is comparison of solid and hollow shafts. A number of questions will appear in GATE examination or any competitive examination on the comparison of the hollow and solid shafts. Which is more beneficial to transmit a given power? Which shaft is beneficial? With a hollow shaft or solid shaft, which is beneficial, which is more economical? That's what the comparison. The comparison is always between a hollow shaft and a solid shaft. So which shaft is more economical to carry a given power? Now I will show you that for a given power, to carry a given power, a hollow shaft is always economical than the solid shaft. A hollow shaft is always economical than the solid shaft. So let us try to obtain them. So actually, before explaining you between these two, I'll explain two things and then I will go to show how these are obtained. So let us first compare the strength. Okay, comparison of solid and hollow shafts. They can be compared for two things. One is comparison by strength. which is stronger. Okay. Comparison by strength. That is, what is the torque carried by hollow shaft? What is the torque carried by solid shaft? Okay, what is the torque carried by solid shaft? So that is one comparison. Another comparison is comparison by weight. What is the weight of the hollow shaft? What is the weight of the solid shaft? So this comparison. These two comparisons are very important. So let us take one by one. Let us first take comparison by strength. Comparison by strength. Both solid and hollow shafts have same length. Let us consider two shafts. One is solid, one is hollow, which have the same length, same material, same weight, and same maximum shear stress. Material is same means shear stress is same. Maximum shear stress is same. So we are comparing for the strength two shafts. One is solid and another one is a hollow shaft, but they have same length, they are same material, and they are same weight. So if strength means what is the torque carried by hollow shaft and what is the torque carried by solid shaft. So if TH is the torque transmitted by the hollow shaft, if TS is the torque transmitted by the solid shaft, let us say TH is the torque transmitted by hollow shaft, H indicates hollow, TS is the torque transmitted by the solid shaft. So the ratio of TH by TS is equal to n square plus 1 by n into under root of n square minus 1. N square plus n 1 by n into under root of n square minus 1. What is n here? N is equal to outer diameter of the hollow shaft divided by inner diameter of the hollow shaft. Outer diameter by inner diameter of the hollow shafts. How this is coming, I will explain you in another 2-3 minutes. But if it is possible, you can remember this. TH by TS is equal to n square plus 1 by n into root of n square minus 1, where n is the ratio of outer diameter to the inner diameter of the hollow shaft. Outer diameter to the inner diameter of the hollow shaft. DH is the external diameter, small dh is the internal diameter of the hollow shaft. So their ratio is n. So if n is the ratio, the ratio of torque carried by hollow shaft and that of the solid shaft is equal to n square plus 1 by n into under root of n square minus 1. So this is the basic formula, comparison formula. So if you can remember this, it is fine for the GATE examination. If you don't remember this also, no problem. I'll tell you in 1 minute how to compare TH and TS. There is no issue. You need not remember this also. If possible, you remember this. It will be easy. N square plus 1 by n into under root of n square minus 1, where n is equal to the ratio of external diameter to internal diameter of the hollow shaft. So here what we are doing, we are comparing the strengths of the hollow shaft and solid shaft. That is the ratio of the torque carried by hollow shaft to that of the solid shaft. So if, for example, if you take n is equal to 2, n is equal to 2, if you substitute here, the ratio of TH by TS is equal to 1.44. 1.44. So you can see hollow shaft for a given material for a same length and same weight. So for same length and same weight for a given material, the hollow shaft carries more torque than the solid shaft. The torque transmitted by the hollow shaft is greater than the solid shaft of same weight. Okay, same weight. If the two shafts are made up of the same weight, then the hollow shaft carries more torque than the solid shaft. That means the hollow shaft is stronger than the solid shaft for a given weight. For a given weight. Weight means cross-sectional area. Weight means nothing but the cross-sectional area because the material is same. Material is same. Density of the material is same for both. So weight is nothing but cross-sectional area because weight is equal to cross-sectional area multiplied by density. Volume multiplied by density. So cross-sectional area into length multiplied by density. Because length and density are same, the comparison of weight is comparison of the cross-sectional areas for the two shafts. So this way you can compare for the strength. So if possible, please remember this. TH by TS is equal to n square plus 1 by n into under root of n square minus 1, where n is equal to external diameter of the hollow shaft to the internal diameter of the hollow shaft. So if it is not possible to remember this, is also no problem. I will tell you. In another one moment, I will tell you how to derive that. That's not a big issue. Similarly, the second comparison is a comparison by weight. The second comparison is comparison by weight. So what is the ratio of weight of a hollow shaft to solid shaft? Now, what will be same now? The two shafts will have the same length, same material. Same material means same maximum shear stress and same torque. Now the two shafts will carry the same torque. Two shafts will carry the same shaft. So the torque carried by hollow shaft and solid shaft is same. So in the previous case, what was same? The weight was same. So that was strength comparison. This is comparison by weight. So if weight is the same now, if weight is if the torque carried is same, what is the ratio of weights? So if WH is weight of hollow shaft and WS is weight of solid shaft, the ratio WH by WS is equal to n square minus 1 into n to the power of 2 by 3 divided by n to the power of 4 minus 1 to the power of 2 by 3. So if possible, you can remember this. If possible, you can remember this. Otherwise, I am going to explain how to get this formula from fundamentals, okay, without remembering this. That also I am telling. I am going to tell you. So if you take n is equal to 2, n is what is n now? N is the ratio of external diameter to internal diameter of the hollow shaft. So if n is equal to 2, for example, WH by WS is equal to 0.7829. So if you substitute in this formula, it is 0.7829. So that means to carry the same amount of torque, to carry the same amount of torque, hollow shaft is lesser weight than the solid shaft. Hollow shaft is lesser weight than the solid shaft. So what does that means? Hollow shaft is lesser weight means what does it mean? Hollow shaft has got lesser cross sectional area. Hollow shaft has got lesser cross sectional area means it is cheaper than the solid. So it is using less weight means we are using lesser material. We are using lesser amount of material. Lesser amount of material is more economical. So to carry the same torque, the hollow shaft is more economical than the solid shaft. Or otherwise, the material required for hollow shaft is less compared to the solid shaft. So the weight of the hollow shaft is comparatively less than the solid shaft for to carry the same amount of twisting moment or the torsion. So if somebody asks you which is an economical section, a hollow section or a solid section in case of twisting moment, you have to say that a hollow section is more economical. So I told you, if you can't remember that formula, I'll tell you how to obtain this formula. First, let us take a weight comparison. Okay, let us take a comparison by strength. Okay, first comparison. Let us take what is the torque carried by hollow shaft and what is the torque carried by solid shaft. So TH by TS. So let us consider a solid circular shaft whose diameter is capital D. A solid circular shaft whose diameter is capital D. Let us consider a hollow circular shaft whose external diameter is D1 and whose internal diameter is D2. The ratio of external diameter D1 to D2 is N. So let us say N is equal to D1 by D2. N is equal to D1 by D2. So here what we are comparing now, we are comparing the strength of the shaft. That is the torque ratio. So for this, the length of the shaft will be same. The material is same, the same material, and also it has got same weight. It has got same weight. So the weight of solid shaft is equal to weight of the hollow shaft. Weight of solid shaft is equal to weight of solid shaft. I know weights can be compared, cross-sectional areas can be compared because weight is nothing but volume into density. Volume into density. Volume is equal to area of cross-section into length into density. Because length and density, length and material are same for this, length and density will be same. So if you compare cross-sectional area, you compare the weights. So WS is equal to WH means AS is equal to AH. That is cross-sectional area of solid section is equal to cross-sectional area of the hollow section. So what is the cross-sectional area of the solid shaft? This diameter D. So pi D square by 4 is the cross-sectional area. So pi D square by 4 is equal to pi by 4 into D1 square minus D2 square. D1 is external diameter, D2 is the internal diameter. So pi by 4 gets cancelled. d square is equal to d1 square minus d2 square. So d square is equal to d1 square minus d2 square. But here we have written n is equal to d1 by d2. N is equal to ratio of d1 by d2. So from this d1 is equal to n times d2. d1 is equal to n times d2. So substitute here a1 d1 square is equal to d1 square is equal to n square d2 square. N square d2 square. So if substitute here, you get a d is equal to d2 into under root of n square minus 1. D is equal to d2 into under root of n square minus 1. So we got d now in terms of d2. So now we know that the torque carried is proportional to polar section modulus. The torque carried for a given material, the torque carried is directly proportional to polar section modulus. So now here TH by TS, the torque carried by hollow shaft to that of solid shaft is nothing but the polar section modulus of the hollow shaft divided by polar section modulus of the solid shaft. So TH by TS is equal to ZP hollow by ZP solid. So what is ZP hollow section? Pi by 16 d1 into d1 to the power of 4 minus d2 to the power of 4. This we know. What is for solid section? It is pi d cubed by 16. So if you put this, pi by 16 gets cancelled. Pi by 16 gets cancelled. We get d1 to the power of 4 minus d to the power of 4 by d1 into d cube. d1 to the power of 4 minus d2 to the power of 4 by d1 into d cube. This is what we are going to get. But what is d2? We know d2 is equal to n times d1. d2 is equal to n times d1. So you substitute that here. d1 to the power of 4 minus d2 to the power of 4. If you substitute that, d2 is equal to n times d1. And d is equal to previous slide. If d is equal to d2 into root of n square minus 1, then if you substitute here, what you are going to guess is d2 to the power of 4 by n to the power of 4 minus 1 by n d2 into d cubes. So otherwise this is equal to n to the power of 4 minus 1 by n into d2 cube by d1 cube. So this is n to the power of 4 minus 1 by n into, again substituting that and simplifying this, you get th by ts is equal to n square plus 1 by n into under root of n square minus 1. So T hollow by T solid is equal to n square plus 1 by n into under root of n square minus 1. So Ts by Th, if you write, it will be n into n square minus 1 by n square plus 1. So whatever way you want, right, you can write this. So similarly, if you take up the comparison by weight, if you take comparison by weight for the same hollow shaft and solid shafts, now what is common? Length is common, material is common, so tau is common, shear stress is common, and both are carrying the same torque. Both are carrying the same torque. So let us consider again a solid shaft of circular diameter d and hollow shaft of diameters d1 and d2. External diameter is d1, internal diameter is equal to d2. So d1 by d2 is equal to L. d1 by d2 is equal to L. So here both the shafts are carrying the same torque. Both the shafts are carrying the same torque. So now we are comparing the weights. What is weight of hollow shaft to weight of solid shafts? That's what we are going to find out. So we know Ts is equal to Th. Ts is equal to Th. We know for the given material, they are proportional to polar section modulus. So polar section modulus of the solid section must be equal to polar section modulus of the hollow section. Same concept. Pi d cube by 16 is equal to pi by 16 d1 into d1 to the power of 4 minus d2 to the power of 4. So from this you directly get d cube is equal to d1 to the power of 4 minus d2 to the power of 4 by d1. Okay. So what d2 is what again? d2 is nothing but n d2. So if you substitute d2 is equal to n d2 in this formula, so you get d cube is equal to d2 to the power of 4 by n to the power of 4 minus 1 by n d2. So this is equal to n to the power of 4 minus 1 by n into d cube. D to the power of 4 is there, d2 is there, so this becomes d2 cubed. d2 cubed. So from this d is equal to cubic root of, so otherwise n to the power of minus 4 minus 1 to the power of 1 by 3 divided by n to the power of 1 by 3 into d2, because this is already 3, 1 by 3 means this is d2. So this is how you get the diameter of the solid shaft, d. Now what is ws by wh? ws by wh is equal to area of solid by area of hollow. Area of solid is pi d square by 4. Area of hollow is pi by 4 into d1 square minus d2 square. So if you simply substitute these two, pi by 4 gets cancelled. You get d square by d1 square minus d2 square. So this is d square by d2 is equal to, if you substitute d1 is d1 by d2 is equal to n. So d1 is equal to n d2. So if you substitute that, you get n to the power of 4 minus 1 to the power of 2 by 3 divided by n to the power of 2 by 3 into n square minus 1. So you get ws by wh, the ratio of the weights of solid shaft to hollow shaft is equal to n to the power of 4 minus 1 to the power of 2 by 3 divided by n to the power of 2 by 3 into n square minus 1. Or if you write wh by ws, this will become numerator, n to the power of 2 by 3 into n square minus 1 divided by n to the power of minus 1 to the power of 2 by 3. So this is how we derive the ratio. So you can see here, if same torque is carried by both the shafts, the weight of solid shaft is more than the hollow shaft. The weight of the solid shaft is more than the hollow shaft. So in that case, more material is required for the solid shaft. Similarly, if weight is equal for solid shaft and hollow shaft, the torque carried by hollow shaft is more than the solid shaft. So that is why hollow circular shafts are better compared to solid shafts in carrying the torsion, in resisting the torsion. So hollow shafts are always more economical than the solid shafts. So these two comparisons, one is comparison for the carrying capacity of the torque, one is comparison for the weight, which are two very important concepts in torque, in the torque, and very favorite topic for many examiners. Very favorite topic for the many examiners. So I am here giving a very important slide. This is a very important slide. So this will give the comparison between the solid shaft and the hollow shaft, where n is external diameter of hollow shaft to the internal diameter of the hollow shafts. Then strength comparison. Weight is same, material is same, length and tau max are same. Material is same means tau max is same, so need not specify. So same weight, same material and same length. Then the comparison between the strengths, torque carried by hollow shaft to the torque carried by solid shaft is equal to n square plus 1 by n into under root of n square minus 1. How to derive this I have already explained now. Similarly, by weight comparison, so torque is same, material is same, length is same. So what is the weight comparison between hollow shaft and solid shaft? So n square minus 1 into n to the power of 2 by 3 divided by n to the power of 4 minus 1 to the power of 2 by 3. Okay, this is how you compare. It's also the strain energy comparison. Which shafts resist the more amount of the strain energy? So same weight, material, length and tau max. This is the first case. For strength comparison, under strength comparison, the strain energy also can be compared. So the strain energy absorbed by hollow shaft UH, that by solid shaft is US is equal to n square plus 1 by small n square. Hence 1 plus n square by n square, or 1 plus 1 by n square. So this is also sometimes very useful. The comparison of the strain energy in the first case, that is strength comparison. For strength comparison, in strength comparison, UH by US is equal to 1 plus n square by n square, or 1 plus 1 by n square. So this is a very important slide, and please do look at this slide, because a lot of questions in GATE examination occur from this topic, that is comparison of hollow shaft and the solid circular shaft. Now let us proceed to composite shafts. If a shaft is made up of two or more shafts, such a shaft is called as a composite shaft. If a shaft is made up of two or more shafts, such a shaft is called as a composite shaft. So there are two types of connection between the two shafts. One is a series connection and one is a parallel connection. Just like we connect pipes in series and pipes in parallel. Similarly, the electrical, we have circuits in series and circuits in parallel. Here also, in shafts also, we have shafts connected in series and shafts connected in parallel. So let us first to understand the concept. The simple concept is important. So don't bother about anything else. Try to understand the concept. So here I am taking the shafts which are connected in series. Here there is shaft 1. This is one shaft. This is connected to other shaft 2 at the junction. Okay, this is fixed at one end. This is fixed at one end, and torque is applied at the other end. Torque is applied at the free end. So if the shafts are connected in series, the important point you have to remember is the composite shaft transmits the same amount of torque. The composite shafts, which is a combination of shaft 1 and 2, will be carrying the same amount of torque T, or otherwise T1, the torque carried by shaft 1, and T2, the torque carried by shaft 2, are both are equal and each is equal to T. This is the concept. Because it's a composite shaft and torque is applied at the free end. The reaction torque that develops at the fixed end is also T in the opposite direction. So each shaft carries the same amount of torque T, or T1 is equal to T2 is equal to applied torque T. T1 is equal to T2 is equal to applied torque T. So this is the first concept. If the shafts are in series, T1 is equal to T2 is equal to T. The second concept you need to remember is the total angle of twist. The total angle of twist at the free end will be is equal to angle of twist for shaft 1 plus angle of twist for shaft 2, or theta is equal to theta 1 plus theta 2. Theta is equal to theta 1 plus theta 2. So this concept you have to keep in mind. First thing for shafts in series, what you have to remember is the torque carried by each shaft is equal. So T1 is equal to T2 is equal to T. The second concept is equal to the angle of twist is sum of the angles of twist. So theta is equal to theta 1 plus theta 2 plus theta 3. How many shafts are there? Okay. So theta is equal to here, theta is equal to theta 1 plus theta 2 because two shafts we are taking. Theta T1 is equal to T2 is equal to T. The second concept. So the concept is very important. The concept is very important. Don't miss the concept. So here the concept is T1 is equal to T2 is equal to T. Theta is equal to theta 1 plus theta 2. But you know what is theta? Theta is equal to TL by GJ. So theta is equal to TL1 by GJ1, G1J1 plus TL2 by G2J2. Or T if you take common, L1 by G1J1 plus L2 by G2J2 like that. If the shafts are made of the same material, then G is also outside. So theta is equal to T by J2, L1 by J1 plus L2 by J2 plus so on. So this is the concept. You need not read. This all comes. The theta is equal to TL by GJ. We know because from the basic torsion equation, T by J is equal to G theta by L. So okay. So from there we get theta is equal to TL by GJ. Theta is equal to TL by GJ. That comes from the basic fundamental equation. Theta is equal to TL by GJ. So what you need to remember is theta is equal to theta 1 plus theta 2. T1 is equal to T2 is equal to T. That is the concept. So understand the concept. So if the shafts are in parallel, now, so you take here, they are fixed at both ends. Fixed at both ends here, and torque is applied at the junction. The torque is applied at the junction. Now the concept is at the junction point, because of the compatibility condition. Now the twist of first torque must be equal to the twist in the second torque. So theta 1 must be equal to theta 2 is equal to theta. See the difference between the series connection and the parallel connection. In the parallel connection now, we have applied torque here. We have applied certain torque here at the junction. So this torque is to be shared by both the shafts, shaft 1 and shaft 2. So here certain amount of resisting torque will develop. Here at the other fixed end, another resisting torque will develop. So if T1 is the torque in first shaft, T2 is the torque in the second shaft. T is to be shared by these two. So T1 plus T2 is equal to T is one concept. T1 plus T2 is equal to T is one concept. And at the junction, theta 1 is equal to theta 2 is the other concept. So what is theta 1? TL by GJ. So T1 L1 by G1 J1 is equal to T2 L2 by G2 J2. So if the shafts are made of the same material, G1 is equal to G2. So T1 L1 by J1 is equal to T2 L2 by J2. So theta is equal to TL by G1 J1 plus G2 J2. So it is total. Theta is equal to TL by G1 J1 plus G2 J2. So this is nothing but theta 1 plus theta 2. Simple substitution. Nothing more. So just try to understand the concept. In case of a series connection, theta is equal to theta 1 plus theta 2. T1 plus T2 is equal to T, torque T. So that is a concept. In case of parallel connection, theta is equal to same. Theta 1 is equal to theta 2. Torque T is equal to T1 plus T2. So that is a concept. So if you have this concept, you can solve any problem. Need not remember any equation. The only thing you need to have the idea is basic torsion equation. Okay. T by J is equal to Fs by, that is tau by R is equal to G theta by L. T by J is equal to Fs by R is equal to G theta by L. If you have that in mind, any of these problems can be solved without any difficulty by understanding the concept itself. If the torque is shared equally by the two shafts, let us say if their symmetry is there, and if the torque is shared equally by the two shafts in parallel connection, then T1 plus T1 is equal to T2 is equal to T, and L1 by J1 is equal to L2 by J2, or otherwise L1 J2 is equal to L2 J1. So this is also coming from the basic concept, because T1 is equal to T2, because T1 is equal to T2. So this automatically leads to L1 by J1 is equal to L2 by J2, because what is the thing? Theta is same here. So G theta TL by GJ is same. So TL by GJ is same. So T is also same means material is also same means T same, G same. So L1 by J1 is equal to L2 by J2. So from this we get this concept. So what is important is you need to remember the concept. That's it. So again here also you see the same shaft fixed at its both ends. Now a torque is applied at certain length L1. So L1, L2. Okay, total length L is equal to L1 plus L2. So at point B, at A it is fixed, at C it is fixed, at B a torque of T is applied. So T1 is developed at A, T2 is developed at A, such that T1 plus T2 is equal to total torque T, and at the junction point, at this point, theta must be same. Theta 1 must be equal to theta 2. So T1 L1 by G1 J1 is equal to T2 L2 by G2 J2. Okay, because the diameter is same, J1 and J2 is same. Okay, J1 and J2 is same. So T1 L1 by G1 must be equal to T2 L2 by G2. Okay, if material is also same, then G1 is also equal to G2. So T1 L1 is equal to T2 L2. T1 L1 is equal to T2 L2. Okay, so this is the concept. This is all the concept. We'll also define one word called as torsional resilience. So torsional energy, okay, torsional resilience is the torsional energy per unit volume. Okay, torsional energy per the unit volume. So it is what work done by the torque. Torsional energy is equal to work done by the torque. So work done by the torque, I said you that time you consider average torque. Average torque into angle of twist is the torsional energy. Average torque is theta by 2 and theta is the angle of twist. So U is equal to half T theta. We know this. U is equal to half into T into theta. Just like in bending, what is the strain energy stored? U is equal to half of M into epsilon. Okay, half of m into epsilon. So the same way here also u is equal to half of t into theta. Half of stress into strain. Similarly here half of t into theta. U is equal to half of t into theta. So for a solid shaft, U is equal to tau square by 4g into volume of the shaft. U becomes tau square by 4g into volume of the shaft. So here you have to substitute T is equal to TL by Nj and T is equal to T by J is equal to tau by R. So from this you get T is equal to R in J by R. So if you substitute all that, you get U is equal to tau square by 4g into volume of the shaft. So the resilience is called strain energy of per unit volume. So torsional energy per unit volume. So torsional energy per unit volume is tau square by 4g. Tau square by 4g. So this tau square by 4g is called as torsional resilience per unit volume. Torsional resilience for the unit volume. Same way for hollow shaft, U is equal to tau square by 4g into d square plus small d square by d square into volume of the shaft. Or per unit volume, it is tau square by 4g into d square plus d square by small d square. D is capital D is the external diameter and small d is the internal diameter of the shaft. So for the same volume, the strain energy stored in a solid shaft divided by strain energy stored in a hollow shaft is equal to d square by capital D square plus small d square. This is what I have given you. Capital D by small d is equal to n. Capital D by small d is equal to n. So that's what I have given you in my previous slide. 1 by 1 plus 1 by n square. I have given you in this slide. See, the energy in hollow shaft to solid shaft 1 plus 1 by n square. This is nothing but coming from this formula. This is coming from d square by d square plus d square. So put d is equal to n times small d. You get 1 plus 1 by n square. That is the ratio of energy stored in solid shaft to the hollow shaft. So that's how. If you just remember the concept, this is all simple derivations from concept. So if you remember the concepts, you can always find out the solution for any given problem. So another important topic in torsion theory is combined bending and torsion. So far now we have studied that the shaft is subjected to only torsion. Now the shaft, let us take a shaft, now it is subjected to torsion and as well as certain loads. Okay. If the shaft is subjected to its own weight, because of its own weight also, in a shaft bending moment occurs. In addition to own weight, there will be some couplings, then some loads that are coming on. So all this will create bending. Okay, all these loads and self weight of the shaft will create bending. So in practice, the shaft is subjected to both bending moment as well as the twisting moment. So due to bending moment, we get compressive stresses and shear stresses, and due to torsion, we get shear stress. Okay, bending produces compressive stresses and tensile stresses, whereas torsion produces pure shear stresses. So because of this, the principal stresses, if a shaft is subjected to a bending moment M and a twisting moment T. Let us say the shaft is subjected to a bending moment M and a twisting moment T. So because of bending moment M, what is the bending stress? The maximum bending stress in a solid circular shaft, M by Z. Okay, M by Z. What is Z? Z is equal to pi d cubed by 32. So the bending stress due to bending moment sigma is equal to 32 m by pi d cubed. 32 m by pi d cubed. This is the bending stress. Sigma 1. This is the 1 stress, bending stress, 32 m by pi d cubed. Sigma x. Sigma y will be 0. Sigma x is 32 m by pi d cubed. Sigma y will be 0. Now what is the shear stress due to torque? If you apply torque T, then the shear stress produced is T by Zp, the polar section modulus. Tau is equal to T by Zp. But what is this polar section modulus for a shaft? It is pi d cube by 16. So this becomes 16T by pi d cube. So due to bending moment, the bending stress is 32 m by pi d cube, Due to twisting moment, the torque is 16 T by pi d cube. So because of this sigma and tau, what are the principal stresses that develop in the shaft? The principal stresses develop in the shaft. We know principal stresses that develop in the shaft is sigma x minus sigma y by 2 plus or minus 1 by 2 under root of sigma x minus sigma y whole square plus 4 tau square. This we know already, but sigma y is equal to 0 here. We have only sigma and tau. Sigma y is equal to 0. So if you substitute here, the principal stresses are sigma by 2 plus or minus half of sigma square plus 4 tau square. If you take plus sign, you get the maximum or major principal stress. If you take minus sign, you get the minor principal stress, and the maximum shear stress is sigma 1 minus sigma 2 by 2. Maximum shear stress is sigma 1 minus sigma 2 by 2. So if you substitute in previous formula, so if you substitute sigma 1 2 is equal to sigma by 2 plus or minus half of under root of sigma square plus 4 tau square. Sigma is equal to 32 m by pi d cube. Tau is equal to 16 t by pi d cube. If you substitute this, you get the principal stresses sigma x. Sigma is the principal stresses is equal to 16 t by pi d cube into m plus or minus under root of m square plus t square. So if a shaft is subjected to a bending moment of m and a twisting moment of t, then the principal stresses are 16 t by pi d cubed into m plus or minus under root of m square plus t square. You need not remember this formula, just like you can derive this, because sigma is equal to m by z. So m by z, that is m by pi d cube by 32. So 32 m by pi d cube. What is tau due to shear stress? Tau due to shear stress is equal to 16 t by pi d cube. You know sigma and t. You know sigma and tau. So the principal stresses are sigma 1 by 2 plus or minus under root half of under root of sigma 1 square plus 4 tau square. So from that you can get what is the principal stresses. But if you can, if you just substitute this is what we are going to get. Sigma is equal to 16 t by pi d cubed into m plus or minus under root of m square plus t square. If you take plus sign, you get major principal stress. If you take minus sign, you get the minor principal stress. So in this connection, we define what is called as an equivalent bending moment or an equivalent torque. An equivalent bending moment is defined like this. So we have both M and T. So both M and T. M is causing bending stresses. T is causing shear stress. Okay, bending stresses and shear stress. Okay. So equivalent bending moment is defined as that bending moment which causes a bending stress equal to major principal stress. A bending stress is equal to major principal stress. So 16 t by pi d cubed into m plus under root of m square plus t square is equal to m equivalent. So if you substitute that, the equivalent bending moment ME is equal to half of m plus under root of m square plus t square. Half of m plus m square plus t square. Similarly, equivalent torque is defined as that torque which produces a shear stress equal to the shear stress due to principal stresses. So sigma 1 minus sigma 2 by 2, if you take, you get equivalent torque. You get equivalent torque is equal to under root of m square plus t square. So this is equivalent bending moment. This is equivalent torque. So the effect of m and t can be replaced by a single me or a single te. Okay, they are called equivalent bending moment and equivalent torque. So tau max is equal to sigma 1 minus sigma 3 by 2. That is half of sigma square plus 4 tau square. So if you substitute sigma is equal to 32 m by pi d cubed and tau is equal to 16 t by pi d cubed, then we get tau max is equal to 16 by pi d cubed into under root of m square plus t square. This is the maximum shear stress. This is the maximum shear stress when a shaft is subjected to both twisting and bending. Now, where is the location of the major principal plane? Tan 2 theta is equal to 2 tau by sigma. tan 2 theta is equal to 2 tau by sigma. So tau is equal to 16 t by pi d cubed. Sigma is equal to 32 m by pi d cubed. So if you substitute this, tan 2 theta is equal to t by m. So from this we get theta, which gives the principal plane location. If you add 45 degrees to that, you get the shear plane, maximum shear plane. And you add 90 degrees to theta, you get the minor principal plane. So this is how you have to analyze a shaft which is subjected to both twisting moment as well as the bending moment. So these are the basic concepts of torsion theory. So now we'll try to solve some of the problems that have appeared in GATE examinations of previous years. So concept is very important. What you need to remember is the concept. So with the concept, you can solve all these problems. A circular solid shaft of span L is equal to 5 meters is fixed at one end and free at the other end. A twisting moment 100 kilonewton meters is applied at the free end. The torsional rigidity Gj is 50,000 kilonewton meter square per radius. Following statements are made for this shaft. The maximum rotation is 0.01 radians. Torsional strain energy is 1. So let us calculate what is maximum rotation and what is the strain energy. So length is 5 meters, twisting moment is 100. Gj is equal to given. So T by J is equal to G theta by L by tau by R. We know theta is equal to TL by Gj. From this, theta is equal to DL by Gj. T is given, L is given, Gj is given. So calculate theta. Theta value is 0.01 radians. What is the other thing? Torsional strain energy. So you know torsional strain energy is equal to half of T theta. U is equal to half of T theta. So half of torque T is given. Theta is 0.01 radians. So it is 0.5. So which statement is correct? Which statement is correct? 1 is correct and 2 is wrong. Statement 1 is true, 2 is false. So answer B is correct. Statement 1 is true, 2 is false. So simple. T by J is equal to G theta by L is equal to tau by R. Concept, nothing more. So this is a composite shaft, okay? This is a composite shaft. Here, the shaft is subjected to a torsion at 2 points, A and B. The torsion is at 2 points, A and B. The torsional rigidity of portion CA and BD is GJ1 and that of portion AB is GJ2. Okay, the rotations of the shaft at point A and B are theta 1 and theta 2. He wants us what is the rotation theta 1 is. He wants us to find out what is the rotation theta 1. B. B is rotation theta 1. So this is the shaft. We have CA of length L, AB of length L and BD of length L. These are three shafts. Here torque T is applied at A and also applied at B. Due to symmetry, the shaft shows that there is no torsion on the portion AB. So there is no torque on AB actually. So in CA there is a torque T, in BD there is a torque D, in AB there is no torque. So torque is acting on each of the end portions AC and BD. So AC there is a torque T, BD there is a torque T. So we know theta is equal to TL by GJ. Torque theta is equal to TL by GJ. So for AC or BD, theta 1 is equal to TL by GJ1. TL by GJ1. So B is the correct answer. So simple. TL by GJ1. That's it. A long shaft of diameter D is subjected to twisting moment T at its ends. The maximum normal stress acting at its cross-sectional area is equal to maximum normal stress. So there is no need to see at all because a long shaft of diameter D is subjected to twisting moment. So there is no other load. It is subjected to only a twisting moment. Twisting moment creates only shear stress. Twisting moment creates only shear stress. What is the shear stress created by twisting moment? 16T by pi d cubed. But here he is not asking the shear stress. He is asking the normal stress. So a torque will not produce any normal stress. So the answer is 0. So there is no need to do anything. The answer is straight away 0. Due to twisting, the shaft is subjected to only shear stress. The maximum and minimum shear stresses in a hollow circular shaft of outer diameter 20 and thickness 2 mm subjected to a torque of 92.7 Newton meters will be what? The maximum and minimum shear stresses. Where does the maximum shear stress will come in a hollow shaft? The maximum shear stress will come at the outer surface, so at capital D, at the outer surface. So the minimum shear stress will come in the inner diameter, so at small d. So we want to calculate that. So what is tau? So we know that T by J is equal to tau by R. T by J is equal to tau by R. What is J? J is pi by 32 d to the power of 4 minus small d to the power of 4. He has given us the capital diameter D, 20. Thickness he has given 2. So internal diameter is equal to 20 minus 2 into 2. Two thicknesses will be there. So 2 into 2 if you remove, it will be 16. So capital D is 20. Small d is equal to 16. So calculate what is polar moment of inertia J. Pi d to the power of 4 minus small d to the power of 4 by 32 gives polar moment of inertia. So now tau max is equal to J by tau max is equal to J by let's see here T by tau is equal to T by J into R. So tau max is equal to T by J into capital D. So T by J into capital D. Okay, sorry, half of the D by 2. From the center we have to take. So 20 divided by 2. So 10. So T by J into 10 is the maximum shear stress. What is the minimum shear stress? Same, T by J into 8. 16 is the... So we want as a comparison. Torque carried is same. Okay, the torque carried is same. So if the torque is torque is increased by 4 times. Okay, right. So we know tau is equal to T by J into R. Tau is equal to T by J into R. So polar moment of inertia is equal to pi d to the power of 4 by 32. Or in terms of the radius, if you take d is equal to 2r, if you substitute this, the polar moment of inertia is equal to pi r to the power of 4 by 2. Pi r to the power of 4 by 2. So from this formula, T by J is equal to tau by R. We can write tau 1 by tau 2. Tau 1 by tau 2 is equal to T1 by T, J by J1, R1 by R. Because tau is equal to T by J into R. T by J into R. Tau is equal to T by J into R. So tau is directly proportional to torque. Tau is directly proportional to R. It is inversely proportional to J. So we have two cases here. Okay, we have two cases here. T1, J1. So tau is equal to T1 by T2 into J2 by J1 into R1 by R2. So if you simply substitute this, you get the answer. Tau 1 is equal to tau by 2. That's it. So basic formula. Again, we are using the basic formula. A hollow circular shaft has an outer diameter of 100 mm and a wall thickness of 25 mm. So internal diameter is also given. So you have to see twice the thickness. The allowable shear stress in the shaft is 125 megapascals. The maximum torque in the shaft can transmit is. So what is the maximum torque that can be transmitted? So what is the torque transmitted? You know, tau is equal to tau by R into J. The torque tau is equal to tau by R into J. So tau is given. The allowable shear stress tau is given as 125. R is equal to outer diameter is 100, so it is 50. Okay, outer diameter is 100, that means it's 50. So tau is equal to T is equal to tau by R into J. J is polar section modulus. Pi by 32 into d to the power of 4 minus small d to the power of 4. Outer diameter is 100 d. Inner diameter is 100 minus 25 into 2, so it is 50. So polar section modulus we got. So you substitute T is equal to tau by R into J, or tau into J by R. That's all. You get the answer. A solid circular shaft of diameter d and length L is fixed at one end and free at the other end. A torque is applied at the free end. What is the shear modulus of the material is G. What is the angle of twist at the free end? Angle of the twist at free end is equal to 16 theta is equal to TL by NJ. Okay, theta is equal to TL by Gj, shear modulus. Okay, TL by G into J is pi d to the power 4 by 32. So 32 TL by pi d to the power 4 by Z. 32 TL by pi d to the power 4 Z. So that's all. Sometimes G is also called as N, shear modulus. So don't get confused. Okay, if they use N also, it is no problem. Sometimes N is also used to call shear modulus. So here theta is equal to TL by Nj or Gj. That is the concept. So substitute what is J, you get the answer. A solid circular beam with radius of 0.25 meters and length of 2 meters is subjected to a twisting moment of 20 about the Z axis at the free end, which is the only load acting as shown in the figure. So 20 kilonewton meters is acting in the Z axis. The shear stress component tau xy at point M in the cross section of the beam at a distance of 1 meter from the fixed end is. So he is asking about the shear stress in xy plane. See here he is saying he has applied a twisting moment in Z plane. Okay, he has applied it in the Z axis. So if you apply a torque in the Z axis, it will have shear stress in YZ or XZ axis. It will have shear stress in YZ and XZ planes only. Okay, because it is applied in the Z plane, this torsion is applied in Z plane, it will produce a shear stress in YZ and XZ planes. But what is asking us tau xy, shear stress in xy plane. So this torque cannot produce any shear stress in xy plane. So the answer is 0. You need not solve anything. The answer is 0. So like just apply the concept. Simple. A hollow circular shaft has an outer diameter of 100 mm and inner diameter of 50 mm. If the allowable shear stress is 125 megapascals, the maximum torque that the shaft can carry, T is equal to tau by R into J, or T is equal to tau into J by R. He has given D1, he has given D2. So calculate what is J, polar section modulus, pi d to the power of 4 by the small d to the power of 4 by 32. You get J. So you apply T is equal to tau into J by R. That's it. R is equal to D1 by 2. So if you substitute 23 kilonewton meters, it's a simple. So let us look at some of mechanical engineering questions in the previous examinations. The outside diameter of the hollow shaft is twice its inside diameter. So D is equal to 2 times small d. The ratio of its torque carrying capacity to that of a solid shaft of the same material and the same outside diameter is. Same material and same outside diameter is. So here the comparison is on the strength, the torque carrying capacity. The comparison is the torque carrying capacity. So you can directly use the formula I have given there. N is equal to here, N is equal to 2. So you can directly use that formula, or otherwise you can see what is D is the outside diameter and D is the inside diameter of the hollow shaft. Okay, so capital D is equal to 2 times D. Torque carrying capacity is directly proportional to polar section modulus. So T1 by T2 is equal to Z1 by Z2. Okay, T1 by T2 is equal to Z1 by Z2. So pi into d to the power of 4 minus small d to the power of 4 by 16d is equal to pi capital D to the power of 4 by 16d. Okay, Z1 by D, Z cube. Z1 polar section modulus of hollow divided by polar section modulus of solid. So here get d to the power of 4 minus small d to the power of 4 by d to the power of 4. But you know, capital D is equal to 2d, 2 times small d. So substitute that here, you get 15 by 16. So answer is A. So even there is no need to remember any formula. Simply you take T1 by T2. It is directly Z1 by Z2. Polar section modulus of first section to hollow section to solid section. That's it. The compound shaft shown is built in at the two ends. It is subjected to a twisting moment T at the middle. What is the ratio of the reaction torque T1 and T2 at the ends? Simple. What is the reaction torque here? T1 and T2. So What is the concept now? The concept is T is equal to T1 plus T2. T is equal to T1 plus T2 and theta at the junction is equal to same. Theta is equal to theta1 plus is equal to theta2. Or T1 L1 by G1 J1 is equal to T2 L2 by G2 J2. Material is same. A length is both is same. So TL by Gj. J is pi d to the power of 4 by 32 d small d. Here T2L by G into J, diameter is 2 times I. So pi into 2d to the power of 4 by 32. So from this you get T1 is equal to T2 by 16 or T1 by T2 is equal to 1 by 16. That is the answer. So if you want actually what is T1 is equal, what is T1 and what is T2? The other equation is T1 plus T2 is equal to total T. T1 plus T2 is equal to total T. So from this you can get T1 by T2. Two shafts A and B are made of the same material. The diameter of the shaft B is twice that of the shaft. Okay, diameter of shaft B is twice that of the shaft A. So DB is equal to 2dA. Okay, the ratio of power which can be transmitted by shaft A to that of shaft B. Oh, very simple. What is that? Say first shaft diameter is dA, the second shaft diameter is dB. dB is equal to 2 times dA. 2 times dA. So we know power transmitted is equal to 2 pi nt by 60,000. 2 pi nt by 60,000. So n is RPM, T is the torque. So torque is directly proportional, the power transmitted is directly proportional to torque. So here 2 pi nt by 60,000 same because the both shafts are rotating at the same speed. So PA by PB is equal to TA by TB. PA by PB is equal to TA by TB. Okay. Or otherwise torque is tau into Z. Okay. Z is proportional to D cubed. Okay. Tau is proportional to D cubed. Or otherwise PA by PB is equal to dA cubed by dB cubed. So, but dB is equal to 2dA. So, if you substitute that, 1 by 8 is the answer. Just using the simple concept. P is 2 pi by 60,000. Power is directly proportional to torque. P is directly proportional to torque. But the torque is proportional to section modulus. But section modulus is proportional to diameter, cube of the diameter. So, the ratio of power transmission is nothing but the ratio of the cube of the diameters. So if you use that concept, you get the answer. A solid shaft can resist a bending moment of 3 kilonewton meters and a twisting moment of 4 kilonewton meters together. So this is a combined bending and torsion. M is equal to 3 kilonewton meters, T is equal to 4 kilonewton meters. Then what is the maximum torque that can be applied? So he is asking us the equivalent torque. Equivalent torque is equal to under root of m square plus t square. M is given as 3, T is given as 4. So under root of m square plus t square is 5 kilonewton meters. So D is the answer. Simple. So maximum shear stress developed on the surface of a solid circular shaft under pure torsion is 240 megapascals. If the shaft diameter is doubled, then the maximum shear stress developed corresponding to the same torque will be. So he wants us the maximum shear stress developed corresponding to same torque when the diameter is doubled. Okay, we know the torsion formula T by J is equal to tau by R or T is equal to tau into J by R or tau into pi d cubed by 16. J by R is nothing but pi d cubed by 16. So from this we know tau is equal to 16T by pi d cubed. 16T by pi d cubed. So here torque is inversely proportional to 1 by d cubed. So torque is proportional to 1 by d cubed. So what is tau? Tau is proportional to 1 by d cubed. So tau 1 by tau 2 is equal to d2 cubed by d1 cubed. Tau 2 by tau 1 is equal to d or tau 2 by tau 1 is equal to d1 cubed by d2 cubes. That's it. So substitute here the diameter is doubled. So d2 is equal to 2d. So substitute here tau 2 by tau 1 is equal to 1 by 8. So tau 1 is 240, 240 by 8 is 30 megapascals is the answer. C is the right answer. Again we are going back to the same equation. T by J is equal to tau by R is equal to G theta by L. So from this Tau is equal to 16T by pi d cubed, or tau is inversely proportional to d cubed, or tau is proportional to 1 by d cubed. That's it. So see here, we are given with a composite shaft, okay, with a composite shafts. The torque of 10 Newton meters is transmitted through a stepped shaft as shown in figure. What is the torsional stiffness of individual sections? The torsional stiffness of individual sections of length Mn, NO and OP are 20, 30 and 60 Newton meters per radian. So he has given us the torsional stiffness. Okay, torsional stiffness. The angular deflection between the ends M and P. Okay, end M and P. So he wants us the total angular deflection. Total angular deflection. He has given us the torsional stiffness. What is meant by torsional stiffness? Torsional stiffness is equal to T by theta. Torsional stiffness is equal to T by theta. So what is theta? T by torsional stiffness. So for Mn portion, the torsional stiffness is T by theta. So 10 by stiffness. Stiffness is 20. So 10 by 20. So this is for Mn portion. For NO portion, the stiffness is 30. So it is 10 by 30. So 1 by 3. T is same. T is same everywhere. All the parts, this shaft or this shaft, this shaft, they are carrying the same torque. They carry the same torque here. So that is why T is same. So if you go to OP portion, what is the stiffness? Stiffness is 30. So what is theta? T by 30. So 10 by 30. So you get what is theta for this portion, theta for this portion, theta for this portion. What is total theta between M and P? It is theta 1 plus theta 2 plus theta 3. So you just sum up them 1 by 2 plus 1 by 2 plus 1 by 3 plus 1 by 6. That's it. That is the answer. 1 radian. So B is the correct answer. A solid circular shaft of 60 mm diameter transmits a torque of 1600 Newton meters. The value of maximum shear stress developed is. So he has given us the power. He has given us the power. A solid circular shaft transmits a torque he has given. Okay, he has given torque T. The value of shear stress is he wants us. Tau is 16T by pi d cubed. Tau is equal to 16T by pi d cubed. What is the big deal? Torque he has given, diameter is given. So simply substitute it, you will get the torque. Direct question. So here you see a composite shaft now. Here you see the composite shaft. The two shafts A, B and BC, both are of same length and diameters D and 2D are made up of the same material. So G also same. They are joined at B through a shaft coupling. Okay. While the ends and C are built in, ends A and C are built in, a twisting moment T is applied to the coupling. A twisting moment T is applied to the coupling. If T and T represents the twisting moments at the ends A and C respectively, or TA and TC, okay, TA and TC represents the twisting moments, then what is the relation between TA and TC? So this is simple. Here the torque carried by this portion is TA, the torque carried by this portion is TC, let us say. So total torque is equal to TA plus TC, okay, the total torque is equal to TA plus TT. At the coupling, at the junction point, the twisting moment must be same. Theta BA must be equal to theta BC. What is theta? Theta is equal to TL by GJ. Okay. Theta is equal to TL by GJ. So TAL by G into pi d to the power of 4 by 32 is equal to TCL by G into pi 2D to the power of 4 by 32 because this is 2D. So from this you get what is the ratio of TA and TC. That's it. So TC is equal to 16 times TA. Answer. So again we are using very simple concept. The theta angle of twist at the junction must be same for both the shafts. That's all. For a circular shaft of diameter D subjected to torque T, the maximum value of the shear stress is 16T by pi d cubed. 16t by pi d cubed. How? T by j is equal to tau by r. J is equal to pi d to the power of 5 by 32. R is equal to d by 2. So if you substitute, tau max is equal to 16t by pi d cubed. A stepped steel shaft shown below is subjected to 10 Newton meters torque. If the modulus of rigidity is 80 gigapascals, the strain energy in the shaft in Newton meters is. You want us to find out the strain energy, half of T into theta. What is the big deal? Okay. Strain energy is equal to half of T into theta. Theta is equal to TL by Gj. So half of T into TL by Gj. So that is nothing but U is equal to T square L by 2 Gj. T square L by 2 Gj. T has given us 10 Newton meters. Modulus of rigidity has given us 80 gigapascals. So polar moment of inertia is pi d to the power of 4 by 32. Okay. So here two shafts are there. So U is equal to this U1 plus U2. So find out what is U for this. T square L by T1 square L1 square by 2 Gj Gj1 plus T2 square L2 square by 2 Gj2. Okay. If you sum up these two, you get total strain energy. U1 plus U2. A solid circular shaft of diameter 100 mm is subjected to an axial stress of 50 megapascals. It is further subjected to a torque of 10 kilonewton meters. The maximum principal stress experienced on the shaft is closest to. So, the bending stress is 50 megapascals. It's subjected to a torque 10. So, due to 10, what is the shear stress we are going to get? Tau is equal to 16t by pi d cubed. So, this is the shear stress. Bending stress he has given us 50 maximum. So, sigma is equal to 50, tau is equal to 50.93. So, apply in principal stresses. Sigma 1 is equal to sigma by 2 plus half of under root of sigma square plus 4 tau square. So, you apply this, you get the major principal stress, 81.7. So, this is the answer. B is the correct answer. A solid circular shaft of diameter D is subjected to a combined bending moment M and torque. The material property to be used for designing the shaft using the relation 16 pi d cubed by under root of m square plus t square is. What is 16 pi d cubed by under root of m square t square is nothing but the shear stress. Is okay? It is nothing but the shear stress. So that is torsional yield strength. So 16 pi d cubed is nothing but the torsional yield strength. 16 by pi d cubed into root of m square plus t square is the maximum shear stress. I have explained you under combined bending assertion. Sigma is equal to 32 by pi d m by pi d cubed. Tau is equal to 16t by pi d cubed. If you substitute for major principal stress or minor principal stress, you get this is the equation. The maximum shear stress is equal to 16 by pi d cubed into under root of m square plus t square. So this is torsional yield strength. A solid shaft of diameter d and length L is fixed at both ends. A torque T0 is applied at distance L by 4 from the left end as shown in the figure below. What is the maximum shear stress in the shaft? What is the maximum shear stress in the shaft? So here we are applying a torque at L by 4. So let us say the portion AC, the torque is T1. Portion BC, the torque is T2. So the total torque is equal to T1 plus T2. So this is the first equilibrium equation. Okay, T is equal to T1 plus T2. Now at junction C, theta 1 is equal to theta 2. So at junction C, theta 1 is equal to theta 2. So you know torque is proportional to 1 by L. So T1 L1 is equal to T2 L2. Okay, so theta 1 is equal to theta 2. You see, if you substitute theta 1 is equal to theta 2, T what is theta? Theta is equal to TL by Gj. So T1 L1 by Gj1 is equal to T2 L2 by Gj2. So two equations to solve for T1 and T2. Okay, two equations to solve for T1 and T2. So from this you get what is the maximum shear stress induced the bark is due to torque T1. So whichever torque is more, that will create the maximum shear stress. So here tau max is equal to 16T by pi d cubed, but that is 3/4 of T naught. So it is T1 is 3/4 of T naught. So that is why T1 produces the maximum shear stress. So substitute 16 is equal to 3 by 4 T naught by pi d cubed. 12 T naught by pi d cubed is the answer. Simple. Out of two torques, which torque is higher? That will produce the maximum shear stress. So find out the ratio of T1 and T2. Find out the ratio of T1 and T2 in terms of T naught, because T1 plus T2 is equal to T naught, theta 1 is equal to theta 2. So with these two equations, you find out what is T1 in terms of T naught. So that if you substitute, you get tau max. A torque T is applied at a free end of a stepped rod of circular section as shown in the figure. The shear modulus of the material of the rod is G. The expression for diameter D to produce the angle of twist T at the free end is, okay, free end at the torque T at the free end is theta 1 plus theta 2. So T1 L1 by G1 J1 plus T2 L2 by G1 J2. So what is theta? What is polar modulus? Pi d to the power of 4 by 32 for one, and pi 2 d to the power of 4 by 32 for the other. So sum of this, theta is equal to TL by GJ for AB, TL by GJ for BC. So from this you get a expression for theta 18 TL by G pi d to the power of 4. So from this D is equal to 18 TL by pi theta G whole to the power of 1 by 4. That's all. So B is the correct answer. So here the concept is theta is equal to theta 1 plus theta 2. Theta 1 is T1 L1 by G1 J1. Theta 2 is equal to T2 L2 by G2 J2. G is same. L is differing. Diameter is differing. So just substitute. A solid circular shaft needs to be designed to transmit a torque of 50 Newton meters. If the allowable shear stress of the material is 140 megapascals, assuming a factor of safety of 2, the minimum allowable design diameter in mm is. We want to find out the diameter. We want to find out the diameter. Allowable shear stress of the material is 140. Allowable shear stress of the material is 140. So what is the factor of safety? Factor of safety is 2. So what is the stress we have to use? The allowable stress we have to use is 140 by 2. 140 by 2. We have to use 140 by 2. So 70 we have to use for tau. So tau maximum shear stress is 16T by pi d cubed. We know 16T by pi d cubed. Maximum shear stress is 16T by pi d cubed. So substitute here. Substitute here. Tau max is 140 by 2. 70 is equal to 16T by pi d cubed. What is D? You get the answer. Okay, you agree. Only thing here is factor of safety you have to divide. You have to divide for factor of safety. That's it. Tau is equal to 16T by pi d cubed, but tau is equal to 140 by 2. So the rest of the things are known. Diameter is unknown. Find out the diameter. Two solid circular shafts of radii R1 and R2 are subjected to same torque. The maximum shear stress developed in the two shafts are tau 1 and tau 2. If R1 by R2 is equal to 2, then what is tau 2 by tau 1? Very simple again. Go by same concept. Radius of two solid circular shafts is R1 and R2. Two shafts are subjected to same torque. So T1 is equal to T2. The maximum shear stress in two shafts is, let us say, tau 1 and tau 2. He has given us R1 by R2 is equal to 2. He is asking us what is tau 2 by tau 1. We know torque T is equal to tau into J by R, or the polar section modulus. So torque is equal to tau into pi d cube by 16, or in terms of R, if you substitute tau into pi r cube by 2. Okay. So because T1 is equal to T2, tau 1 pi r1 cubed by 2 must be equal to tau 2 into pi r2 cubed by 2. So from this, tau 2 by tau 1 is equal to r1 cubed by r2 cubed. So tau 2 by 2 1 is equal to 2 cubed. That is answer is 8. This is again a stepped shaft subjected to twisting moment applied at B. Assume shear modulus as 77. What is the angle of twist at C? So he wants us to find out what is the angle of twist. So what is the angle of twist at the end? The angle of twist is same between B and C, since there is no torsion induced in BC. So torque is 10 and diameter of the shaft is 20, length of the shaft is 500, theta is equal to TL by GJ. So substitute for TLGJ, J is pi d to the power of 4 by 32. So you get a theta in degrees, 0.237. You get in radians, that you multiply by 180 by pi, you get in degrees. He is asking in degrees, so multiply into 180 by pi, you get in degrees. A hollow shaft of 1 meter length is designed to transmit a power of 30 kilowatts at 700 rpm. The maximum permissible angle of twist in the shaft is 1 degree. The inner diameter of the shaft is 0.7 times the outer diameter. The modulus of rigidity is 80 gigapascals. The outside diameter of the shaft is, so he has given capital D by D. Okay, small d by D has given us 0.7. He wants us to find out capital D, outer diameter. He has given us the length 1 meter. Power transmitted is he has given. He has given what is the rotational speed 700 rpm. He has given us theta also. So we want to find out the outer diameter of the shaft. Okay, so modulus of rigidity is given. First we know P is equal to 2 pi nt by 60,000. Okay, so P has given, he has given Na has given. So from this we get torque in Newton meters. We get torque in Newton meters. We know polar moment of inertia is pi by 32 into d1 to the power of 4 minus d2 to the power of 4. But d2 is equal to 0.7 times d. So if you substitute, you get j is equal to 0.0746 d to the power of 4. We know theta is equal to TL by GJ. Okay, you know theta is equal to TL by GJ, but he has given degrees, we want to convert into radians. So 1 degree converted into radians is equal to 1 into pi by 180. So this is theta. This is equal to TL by GJ. So substitute T, 409.25 Newton meters. So convert into mm, multiply with 1000. Length is 1 meter, convert it to mm, multiplied by 1000. G is he has given, so convert it into the units. And J is the polar section modulus, 0.04676 d to the power of 4. So the only unknown in this problem is D. So solve for D, 44.52 mm is the answer. So again, a hollow shaft of D0 is equal to 2dI, where D0 and dI are the outer and inner diameters. Needs to transmit 20 kilowatts power at 3000 rpm. The maximum permissible shear stress is 30 megapascals. What is D0? In the previous problem, he has given twist, angular twist. In the present problem, he is giving shear stress. Okay. Again, the same thing. Okay. Power transmitted is 20 kilonewtons. So RPM is 3000. So from this, you get P is equal to 2 pi nt by 60,000. He has given you power, so you get torque T. Torque T is equal to 63.66. You get Z, polar section modulus, is 16 by pi by 16 into D0 into D to the power of D0 4 minus small d to the power of 4. Here you substitute outer diameter is 2 times inner diameter. So you get 0.1841 D0 cubed. Okay. So tau max is equal to tau by Z, tau by G, Z. So polar section modulus. Already we have got T. T is 63.66. 63.66 into 10 cube divided by polar section modulus is equal to 0.1841 D0 cube. So if you substitute, only unknown is D0. Solve for D0, you get the answer. So a rigid horizontal rod of length 2L is fixed to a circular cylinder of radius R. The vertical forces of magnitude P are applied at the two ends as shown in the figure. The shear modulus for the cylinder is G and the Young's modulus is E. What is the vertical deflection at the point A? So he wants us to find out the vertical deflection at point A. So to find out the vertical deflection at point A, we have to first find out theta here. Okay, if you find out theta, then theta into L will give you what is the vertical deflection at point A. So first we have to find out theta. Okay, first we have to find out theta. Theta is equal to TL by GJ. So apply T is equal to 2PL. Okay, see here what is torque. It is subjected to P on one side and P on the other side. So PL plus PL, 2PL is the torque. So T is equal to 2PL. So 2PL into L by G into J. J is equal to, in terms of radius, pi r to the power of 4 by 2. So this is what you are going to get theta. So deflection at point A is equal to theta into L. So multiply this with L. 4PL cube by pi r to the power of 4G is the answer. A shaft with a circular cross section is subjected to pure twisting moment. The ratio of the maximum shear stress to the largest principal stress is. Very simple question. Shaft is subjected to pure twisting moment. So when pure twisting moment, there is only shear stress. There is only shear stress. There is no bending stress. So when there is no bending stress, the largest principal stress, so sigma is equal to, what is sigma? What is sigma 1 2? Sigma 1 2 is equal to 16 by pi d cubed into m plus under root of m square plus t square. So in this m is 0. Okay, there is m is 0. There is no m. There is only twisting moment. So we have only tau is only the shear stress. So the major principal stress is nothing but the shear stress tau. So the answer is ratio is 1. There is no bending. It is pure twisting. So sigma and tau, we have the principal stresses. If sigma is the bending stress, tau is the shearing stress, then the principal stresses is sigma by 2 plus or minus under root of half of under root of sigma square plus 4 tau square. So in this case, sigma is equal to 0. So sigma 1 is nothing but tau. So tau max by sigma 1 is, both are same, tau by tau. So that is equal to 1. So that is the answer. So like this, by using the concepts of twisting moment, by using the concepts of the twisting moment, you can solve any problem. So here I have given so many problems I have solved it today. Did we use any remembering capacity? Our mind's remembering capacity, did we use? No. We only use the equation is T by J is equal to tau by R is equal to G theta by L. That is the only thing we need to remember. The rest of the things are only by concept. So only by concepts we have solved so many problems. So that's what very interesting in this particular subject. I always advise the students, don't try to remember anything except the fundamental concept. So in bending stresses also I have defined m by I is equal to f by y, the bending sigma by y is equal to e by r. So with that formula, we could solve every problem in the bending stress. So we need to have the fundamental concept. So just here also, with fundamental torsion equation, T by J is equal to G theta by L is equal to tau by R. With the fundamental equation, we can solve any problem given in the GATE examination or in whatever examination. So keeping the concept is very important. Keeping the concept in mind is very important. Don't remember anything. So this way we can solve any problem in GATE examinations. So that's what I wanted to explain you in this particular chapter. Hope you enjoyed today's presentation. Hope you have enjoyed today's presentation, and tomorrow we are going to deal. Tomorrow we are going to deal. Tomorrow we are going to deal with columns. Columns. We are going to deal columns. So everybody come prepare to understand the column chapter. Okay, Euler's theory, Euler's buckling theory. Okay, long column, short columns. We just go through whatever material is available with you about the columns. So tomorrow let us discuss about the columns, and I wish you all a very pleasant evening today, and let us meet tomorrow. Have a nice evening. Take care of yourself and your family. Bye bye. Take care. See you tomorrow afternoon at 3 p.m. Thank you very much.